I recently made a video where I came up with a solution to the infinite 1D infinite square well. This is your classic quantum mechanics problem, and I'm going to redo the problem numerically, but let's just review what we did before. And I'm not going to go over the solution. The link down to this video is down below because it takes a while. We start with the Schrodinger equation in one dimension. This says that there's some wave function psi that solves this differential equation that kind of looks like the wave equation, but not. Here we have I is the imaginary number, h bar is a constant, 2m the mass. But it says there's a relationship between a time relationship and the second derivative with respect to space, and this v psi is due to the basic. It's from the Hamiltonian, but if we have an infinite square well, then we confine a particle to this region of space between two infinite potentials, and we assume that it can't exist over here because the potential is infinity. It couldn't get in there. So if we're just looking for a solution in this space from x equals 0 to x equal a, then that v term is 0, and so we have that differential equation, which is a little bit easier. We can solve that by first assuming you can separate it into a time function f of t and a space function psi of x. It's lowercase psi. The time part's not difficult. I'm not going to do it, but it's there. It turns out that it doesn't super matter all the time, but we're not going to deal with time today. And so how do you solve the space part right here? You can do it. It's not too difficult by guessing a solution and setting the boundary conditions, and you get this for the solution a sine k a, where k depends. In order to make this boundary condition satisfied, k has to be a multiple of pi, n pi over a, and this sets limits on the energy, which I didn't put here. Why did I not put the energy? Let's see, E, right here. So you can solve this for E. I get En equals k squared h bar squared over 2m, and because we're going to need this for later. And then if I put in this for k, I get, that's h bar squared. I get n squared pi squared h bar squared over 2m a squared. So that tells me my energy values that solve this problem. But the fun thing is to do this numerically, to not use a differential equation, but to use essentially a computer program to solve this, to write code to solve this. So let me just tell you really briefly how you would solve a numerical problem that you've done before, the simple harmonic oscillator. This is a little tilted. Follow me. Okay. Imagine that I have a very simple situation of a mass on a spring like that, and I can say that the force in the x direction is negative kx. This is the easiest case, and that would be ma. And I can write that as negative kx equals m, the second derivative of x with respect to time, right? Because the acceleration is the second derivative. The first derivative of position is velocity. So I have a differential equation. How do I solve that? We like to write this as a equals negative k over m. X, v is going to be the derivative of the position. So dx dt, like that. Or what we really do is to break this into short time intervals, delta t. So I'm going to write this as delta x over delta t. And then during each time interval, I can calculate the acceleration. I can use that to update the velocity, because a is dv dt, delta v delta t, and then update the position. And if you haven't seen this before, I'll put a link to my favorite video version of this. But here's the basic game plan. Number 1, calculate a. A is negative k over mx. 2, use this value, and this is all for delta t equals 0.01 seconds or something like that. Number 2, if I know that, if I assume the acceleration is constant, which it's not, I can use this to say that this is v2 minus v1 over delta t, where v2 is the velocity at the end of the time interval. That's at the beginning. I can use that to solve for v2, like that. I just solved this for v2. And I get the velocity at the end of the time interval based on the velocity at the beginning and the acceleration, which I just calculated. And then I can do the same thing with the definition of velocity and position, and I get x2 is x1 plus v delta t. And then I just repeat this again. And that's my basic numerical calculation. Now, how do we do that for the Schrodinger equation? Because it's a little bit different here. So let's start with this differential equation. I'm just going to write that down. Second derivative of psi with respect to x equals negative 2me over h bar squared psi. That's my equation I want to solve. And so I don't have derivatives with time. I have derivatives with respect to x. So right there, I'm going to break this into pieces of x. Let's say 0.01. It doesn't really matter. I am going to need numbers, though. Right? So I'm going to have to pick like h bar equals 1, a equals 1. Let's put m equals 1. I'm just going to use those values just because it's easier. Let's write this in a slightly different form. I'm going to write this as psi double dot for the second derivative of psi with respect to space. And that's going to be equal to negative 2me over h bar squared psi. I can do that. If I break this into small steps, I can calculate psi double dot if I know what psi is. And then I can also set this equal to psi double dot is delta psi dot delta x, right? Because it's the derivative of psi with respect to space. And this would be psi 2 dot minus psi 1 dot over delta x. All I did was just, instead of put delta psi, I just, psi 2 dot is the wave function at the end of the space, and that's at the beginning. And I can solve this for psi 2 dot. Psi 2 dot is psi 1 dot plus psi double dot delta x. And then I'm going to put this right up here too, because this is my step 2. Step 1 is psi double dot is negative 2me over h bar squared psi. That's number 1. Now, after that, I can go down here. I need to find psi. So I can do the same thing. I could say psi dot is delta psi delta x, or psi 2 minus psi 1 over delta x. And then I can solve this for psi 2, and this is going to be step 3. Psi 2 is psi 1, that's a psi, plus psi dot delta x. And then I just repeat the whole thing. But there's a problem. There's a really big problem, right? Because for the simple harmonic oscillator, this works fine because I know the initial time. I know the initial, I need to know the initial conditions. So I need to know x dot at 0 is 0, the velocity. I need to know the initial position. Let's say it's 0.02, whatever. I need to know those initial conditions. I have 2 values right there. I know those initial conditions. Now, if I do this, if I want to do this from not in time but space, I'm going to go from here, right there, starting at x equals 0, over to x equals a. And I know that the wave function psi has to be 0 right here, and it has to be 0 right there. I know that has to be true. But if I'm breaking this into pieces of x, and I start with psi 0 equals 0, that's fine. Okay, I can calculate psi double dot, except I don't know E. That's a problem. Don't know E. That's bad. Now down here, I also don't know the initial derivative of psi, so I'm going to have to pick that. Pick psi, I guess I should call it, I'm switching back and forth between those two. The initial psi, I don't know it, right? And then I can't just put in my value, my boundary condition, because I haven't calculated that yet. I'm going to calculate this, then here, then there, and so forth. And so what I'm going to do is to just do this and see what happens. And you'll see that it's not going to work. But we can fix that. Okay. So it kind of looks like your normal numerical calculation, but with a twist. Because I know where it has to end up instead of knowing all the conditions where it starts. So in the normal classical mechanics, we deal with initial conditions, but this is a boundary value problem. I need to know the value at the boundaries, so it doesn't quite work. This is not the best method to solve this problem, but it does work, and I think it helps us understand what's going on. Let's just jump into Python and start doing it and see what happens. It's going to be fun. I think it's going to be fun. Let me change it. I'm going to have fun. Let's start off, we need a graph. G1 equals graph, because I'm gonna plot that wave function. So title equals, let's just say psi. 1D, well, let's put 1D well. X title is going to be X, and then Y title is going to be psi. I need to put this width equals 450, height equals 200. Otherwise, it just doesn't show up very well. F1 equals G curve, color equals color.blue. Now I need my values. H bar is 1, mass is 1. And you can pick actually real values for this, but then you have to think about how you break this thing up. I'm just picking 1 because you can change those things later. A equals 1. Did I have something else? That's it. I'm going to be moving along in the x direction, so I need to start with my x value of 0, x equals 0, and I need a dx. How far do I move? Let's just put this at 0.01. We can change that later. Is this big enough? I feel like it's not big enough. There, it's better. I also need my initial psi, 0. It's going to start at 0. It has to. That's a boundary. I need to know my initial derivative psi dot. So I'm going to call that d psi for the first dot. And I'm going to set that equal to 1. I also need to know the energy, which I don't know. So I'm just going to put that at 0. I'm just picking. I'm just picking it. Now let's just go through and say while x is less than a, do the following. Number 1, calculate psi double dot. So psi double dot, I'm going to call that d psi for double derivative. And it's going to be equal to my equation right here. It's -2 times m times e times psi divided by h bar. That's just the equation. Once I know psi double dot, I can use that to calculate psi dot. So d psi equals d psi plus d psi times dx. Remember, we're dealing with space. It's a space derivative here. And just a reminder, in Python, I am taking the value of d psi, I'm adding this to it, and I'm making that the new value of d psi. So that updates the variable. I don't need to deal with indexes 1, 2, 3, 4, 5, 6, 7, stuff like that. I can just do that. Now I can update psi. Psi equals psi plus d psi times dx. And now I can update x. X equals x plus dx. And let's plot that. F1 dot plot x and psi. And let's run this thing and see what happens, if it even runs. There. Okay. So here's my well. I went from one end to the other. And we want our boundary conditions say that the function has to be equal to 0 right here, but it's not. It's equal to that. Well, we don't have too many options here, so one thing we can do is just change the energy. I'm just going to change the energy. Let's just put the energy is equal to 1. I'm just picking a value. Let's just see what happens. If I start with an energy of 1, you see it's not straight anymore. I could keep doing this. I could pick an energy of 5. Let's do 4. And it's very close, right? 'Cause what am I looking for? I'm looking for a wave function that starts at 0 and ends at 0 over here. And this is really close. Now let's go with 5. And, you know, this method of just changing the energy until you get what you want, that's pretty close to what I want, is fine. It's not the best, but it works, right? And you can see what I'm doing here. I'm changing the energy and shooting for the boundary. That's why this is called the shooting method. Okay. Let's automate this though. let's do this manually. One of the things I do want to do is to print the, let's calculate E theoretical. I'm just using my equation over here. I said that was E1 would be, let's say n is equal to 1. So the energy, the theoretical energy is n squared times pi squared times h bar squared divided by 2 times m times a squared. And let's print that. E t equals ET. It's not in real units, so it doesn't really matter. And then we can see I was very close. 5 is very close. So let's put this energy back to 0. And now I want to say what I'm going to do is I'm going to run it. I'm going to check if my wave function's at 0 at the end. And if it's not, I'm going to increase my value of E. So what value of E should I increase by? Let's say E is 0.01. I'm just picking, right? And you can, depending on how accurate you want your simulations, your calculations to be, dictates the size of that. Also, your size step of your spacing is important too. But I'm going to leave it at 0.01 just so it runs fine and no one gets in a tizzy. So what I'm going to do is to run this calculation for that energy, and then I'm going to see if the end value is 0. And if it's not, I'm going to increase E and do it again. So let's make a new variable called psi final equals 1. I'm just going to pick it. And after I run this calculation, I'm not gonna do that right there. What I am going to do is set, once I get to the end of the while loop, I'm going to say psi final equals psi. And let's, up here, I will say while psi final is greater than 0. Right? And I already know the psi final is greater than 0. You could do a better check here. I'm not doing the best program. I'm doing a program to help you understand what's going on. And I need to indent all this stuff. Tab. I'm going to put a rate statement here. So rate just makes it only do 100 loops per second. So we can animate this. I'm going to make an animated graph. Before I start the loop over, I need to reset my values, right? I'm going to say psi x equals 0, psi equals 0, d psi equals 1. That's what I picked before. And after I get done, I'm going to also increase the value of the energy. E equals E plus dE. No, the E. That should do it. Now, I want to make a graph. I haven't saved this. Let's save this. Because you're going to want the code. I know it. Shooting method 1. To make a graph, I'm going to make the graph, I'm going to plot psi. But psi is going to change when I change energy. So I want to animate that graph. So here's how you animate that graph. Down here, let's make a new list called F1 data, and it's an empty list. I'm going to empty it at the beginning of the loop. In the loop, instead of plotting, why is that not scrolling down? Instead of plotting the value, I'm just going to add the value to my F1 data list. F1 data equals F1 data plus X psi. And then once I'm done with this loop, then I can plot it. Let's just put it right. It doesn't really matter which one. So this, you can do an animated graph. F1 dot data equals F1 data. So now when I'm going to plot the whole thing at once. I think this should work, but you never know. It's a bit much. Yeah, there we go. So you see the energy values are increasing and the final wave function's decreasing, and I'm shooting for that final point. I didn't print out the energy. I should have done that. There. It's done. So let's print out the final energy once we're done. And let's increase this rate because that was too slow. 300. So once we're done, oops, DE, print E calc equals E. And let's run it again. And there you can see my calculated energy is 4.95. My theoretical is 4.93. I mean, close enough. I could get better if I wanted to. I just don't. This is a proof of concept. What about the next energy level? Well, let's just increase the energy. Start at 4.95 because I know at 4.95, I know that it's going to be below. It's going to keep going below that. So psi final is going to be negative, and I want to do psi final until it gets back up until it's greater. Let's see, psi final, while psi final is less than 0, it changes to less than. Let's see if this works. Oh, it didn't. Okay, let's change this to energy of just a little bit greater. No, it's not working. Okay. So, oh, I didn't. That's why. I said psi final is 1. So it's going to change that value really quickly. It doesn't really matter. So now as I increase the energy, my wave function comes back up to 0, and you can see I'm getting my second energy level, and this is sine of n pi, or where n is equal to 2. And the energy I get is 19.7. We could calculate that and print it out, but I'm not going to do that. If I wanted to, I could also plot the probability density, psi star psi, which would just be the square of this. And I want to point out something really important. I don't have a function. This looks like a sine graph, but it's not. It's just data. And I do have a problem. I have not normalized my function. And so the question is, how would you normalize this? Well, normally we normalize things by integrating over all space and setting that equal to 1. And I can't integrate because I don't have a function. I have data. So I'm going to have to do a numerical integral. I'm not going to do that in this video. I'll do that in another video. But we can integrate numerically psi star psi and set that equal to 1 and use that to adjust what we have one other property that we can adjust here, right? We can adjust d psi, the starting slope. That's the only thing I can adjust. I've already adjusted the energy to get the wave function to work. The other thing I can do is adjust the initial slope of the wave function. And that's what I'm going to change to get the thing normalized. Now let's look at one more question here. Why would you do this? Because the solution to the 1D infinite square well is not that complicated. So what's the advantage of doing it this way with the shooting method, which is not the best way, but I think it does help us understand. Well, there's a couple of really important nice things here. What if I don't have a flat square well? What if I have a bump in the middle? What if the potential is not 0 everywhere? Or what if it's a harmonic oscillator? Or what if the potential is anything? Well, this doesn't care, right? The only thing that would change here is that this part right here would change. I would have a potential function in there too. And I can easily do that if I have a number for the potential. I can plug it in there and I can get a new solution. And again, I don't have a function for that solution, but I have data and I can plot the whole thing. What if I don't have infinite walls? What if I have, finite value potential walls and the function goes into those other spaces? I can do that too. You can do that on paper also. But this method doesn't care about those things. As long as we meet the boundary conditions, the boundary conditions are much harder in a finite square well because you're saying the wave function that negative infinity is 0, which is, you're not going to do that numerically. But we can make that work. And I will do that. And that's where this comes into play. This is what makes this method nice. It's like I said, there is a better method to solve this. But I think this one, if you're coming from introductory physics, it makes the most sense, right? Because it's just like solving other physics problems numerically where you break it into small steps, and then you just, update the things along those steps and you go for it. The code for this is going to be down below. My link to my solution for the Schrodinger's equation, the normal traditional way, is down below too. And then I will do normalization, but I'm going to save that for another one because we have to do a numerical integral, which is fun. Okay, but I'll save that for later.